The recording. Okay, so today we are going to look at some issues around demand, right? Demand for environmental goods. Okay, so now we'd already talked about last time. We had set up our model. And we have emissions and the marginal savings is, let's say it's equal to 12 minus E, and marginal damage is equal to 3 times E, or say 2 times E, right? So we can graph that. And there's the marginal savings, right? And so that the unregulated level of emissions will be 12, right? And then we put in the marginal damage schedule. And substituting in, we can see that the optimal level of emissions, 12 minus E equals 2E, 12 equals 3E, E equals 4. And the marginal damage is given by 8, okay? So what we can do is define E, emissions will equal 12 minus abatement A. So if I substitute that into the marginal savings, I get marginal savings equals 12 minus E, 12 minus A. Marginal savings is simply A. Marginal damage, we said, was equal to 2E, which is equal to 2 times 12 minus A, right? So that equals 24 minus 2A, and that tells me the marginal benefit of abatement. So we have the marginal damage of emissions. So the more emissions we have, the more damage is incurred. Alternatively, the reverse image is the marginal benefit of having no emissions or abatement, given by 24 minus 2a by substitution. And what that means is graphically, if we draw it this way, and then we have abatement on this axis, money on this axis, and we have the marginal benefit of abatement, and the marginal abatement cost, the marginal cost of abatement is given by this line. And when we solve for that, we get that abatement is 8. So we engage in 8 units of abatement, which leaves 4 units of E. Or in the first graph, we got rid of 8 units of emissions. So that gives us A equals 8. Now we can look at the social cost. So total damages is this blue triangle, and it is half the base times the height. So base is 4, height is 8. 8 times 4, 32 is 16. And total abatement cost is given by the area under the marginal savings schedule. And that area is 32, half the base times the height. 8 times 8, 64 divided by 2, 32. So the firm, the polluting firm, sees that their total abatement cost is 32. Total damages to the environment is 16. And the total social cost is 48. So social cost is total abatement cost plus total damages. That represents social resources that are redirected because of the existence of emissions, okay? And we can go to the second graph. And if we want to know the total abatement costs, 32. And we did not get rid of all the emissions, so we have 16 is the triangle associated with emissions of 4. So damages are 16, okay? Now, the marginal benefit. So the marginal benefit of abatement is directly related to demand for environmental, quality. Okay, so we're starting to look at the demand side. And one of the challenges is that normally, right, we have the benefit of a good is what gives us our demand. And it can also be viewed as willingness to pay. And that feeds into a market. And that market then will set price. So that's how a normal market system works. The benefit of a good translates to demand. Demand leads to a willingness to pay, which sets the market price. But what if there is no market? Right? So then where does the price come from? Okay. So the problem with the environment is that it tends to be made up of a non-market good. So there is no well-defined market for clean air, or for the most part, clean water. Even though we do sell water in the grocery stores, it is basically a decentralized system. Okay, now, how do we deal with non-market goods? We know that that value exists. How? Well, one example is British properties. In West Vancouver. Okay, this is a very unique, distinct patch of real estate. And the way it works, so we have Mount Baker to the south. In West Van, we have the property coming down to the ocean. Okay. So the ocean separates West Van through the Burrard Inlet from the rest of Vancouver. And on a clear day, I can build a house and I can have a view of Mount Baker. Unless somebody else comes along and builds an even bigger house in front of my house. And this second house blocks my view. Okay, here is what makes British properties unique. The view of Mount Baker adds to the value of the property. So British properties includes the view in the deed. Okay. That means that the person in house number 1 who was there first and built their house, who finds that they're being blocked by house number 2, they can call the city, and the city will tell house number 2 that you cannot build higher than the first house view, so that you do not block the view. So the view becomes part of the property right. So now house number 1 will never have a house number 2 built that blocks its view. That greatly increases the value of house number 1. So house number 1 increases in value due to protection of the view. So we can say, how much is a view worth? Well, we can go and look at all sorts of neighborhoods with similar houses and compare the ones that have the property right and built in versus like British Properties versus the ones that do not, and see the difference. Okay. Now, example 2, Snake River. And then in the 1970s, and this is in Oregon, okay, was they were looking at whether they should build a dam. Okay, so they had they knew the value of the electricity that would come from the dam. They did not know the value of Snake River as recreation. Okay. So the economists were asked to come in and answer the question, is this Snake River better off as a dam or is it better off as recreational property? And what they did was they took the annual demand right? So this was for use of Snake River as a recreational. So people would kayak, they would fish, they would camp, and all of it was free. So what they did was they took the area under the demand curve and estimated it. Okay. And let's suppose that the consumer surplus was equal to X. Okay. So then they said the net present value will be equal to simply X divided by the interest rate. Okay. So if X equals $1 million a year, and the interest rate is equal to 0.05 or 5%, then the net present value will be, say, 20 million, right? They would compare that number, 20 million, as recreation net present value of the recreation to the price of the dam. In this case, it turned out that the recreational property value was greater than the value of the dam, and they opted to not build the dam because the economics said it was more valuable as recreational property. Okay. So that's another example. Another example 3, closer to home, is Stanley Park. Everyone's familiar with Stanley Park, right? And when we look at Falls Creek, right? And we have Stanley Park, right? And then we have the West End. And you have your seawall all the way around. And it carries on out to Kitsilano, carries down towards the Second Narrows. And otherwise, we have this big green park in the middle of downtown Vancouver. And it is one of the more scenic things Vancouver has to offer. And it is a tourist attraction. Okay. So we have to compare the real estate value to the value as a park. Problem is that the park is, for the most part, free. There's a couple of paid events in the park, but for the most part, you can enter the park for free. Okay. So this gives rise to the question of how do we value non-market goods? Right? And there's different ways that people go about this. Okay, so A, we engage in what's known as defensive expenditures. Okay, so we buy sunscreen. We buy bottled water. Right? We put in some kind of filter. These are what are known as defensive expenditures. They're money invested to protect us from the negative effects of something in the environment. So one method is to use defensive expenditures to assess value. How much people are willing to pay to avoid something, okay? The other method, B, that we look at is known as hedonic pricing models. And hedonic pricing models tend to, right, net out all explainable value, right? So we have two houses, A and B. And house A is in a cleaner environment. And we want to know is how much people value the cleaner environment. So we've got these two houses. So we look at the attributes of the two houses. So we have square footage, size of the house, bus routes, roads, schools, stores, all the things that you look for when you shop for a house. How close are they to school? How much square footage? Is there a bus route? Are we on quiet roads or busy roads? Is there any stores nearby? Okay. So we get the price of A and we have the price of house B. Okay. So we adjust for all the attributes until we can explain the value of each house based on square footage, bus routes, roads, schools, and bridges and stores. Okay. So after the adjustment, the difference between price of house A minus price of B equals the willingness to pay for a cleaner location. Okay, so we know these two houses have their own price. We adjust the prices to explain why they're different based on square footage. We then estimate why the two prices are different due to buses and roads and schools. And after we've adjusted for everything we can explain, then we look at what's left over. And what's left over, if we've accounted for everything but the environment, whatever's left over must be the environment. So, yeah, account for everything except the environment. Whatever's left is due the demand for environment. So, okay. So this is what's known as hedonic pricing models. It is something that economists do all the time. It's a simple statistics exercise. It's something that can be calculated using something like Microsoft Excel. Okay. Then we can have travel costs. And they are basically a variation of defensive expenditures. So we have a town, we have Lake A, and we have Lake B. And Lake B is cleaner than Lake A. Okay. But Lake A is only 10 kilometers from the town, whereas the Lake B is 70 kilometers from the town. Okay. So some people will travel an extra 60 kilometers to get to a clean lake. So we can look at the value of the transportation. So, and the value is equal to travel time. So whatever it takes to go the extra 60 kilometers. And we multiply that by the opportunity cost of time. Sometimes referred to as the wage. So this is one way of calculating, is to look at these travel costs, okay? So 3 methods so far: defensive expenditures, B is hedonic pricing approach, C is travel costs, and then D is direct survey data. Okay. And that gives rise to 2 questions. Right? 1, how much would you pay to save Stanley Park? Okay, so the government comes along and they say, we're going to plow Stanley Park flat and build up condos unless you pay to protect it. People say how much they're willing to pay to protect it. And that's the number we use to decide whether or not to keep the park. Or we can ask an alternative question, which is, how much is required to accept the loss of Stanley Park? Right? Okay, so 2 ways of asking this question. 1, how much would you pay to protect Stanley Park? And 2, how much are you willing to accept as compensation for losing Stanley Park? And this is known as willingness to pay versus willingness to accept. Okay, so my willingness to pay for something versus my willingness to accept. The technical terminology for this is CV, compensating variation, or EV, equivalent variation. Okay. Now, the interesting thing is both of these questions are designed to give us a value of Stanley Park. The problem is they are two different questions, and quite often they have two different answers. And before you ask about it, this is independent of people's willingness to lie about how much they value a park. This is, even if we correct for strategic answering, there is a difference between willingness to pay and willingness to accept, okay? So what we need to do is digress to a consumer theory review, just so everybody understands this. So in consumer theory, we know that people want to maximize their utility of two goods, X and Y, subject to the price of X times X plus the price of Y times Y is less than or equal to some kind of budget. Okay. So B is the budget. PX and PY are the relative prices. Okay. Now, for simplicity, we usually let PY equal 1. Okay. Now, if we look on our XY axes and put in put in the budget line. Then our budget, B equals PXX equal plus PYY. And if X equals 0, Y is equal to B over PY. And if Y equals 0, X equals B over PX. Okay, so, and B over PX is just the budget divided by the price of X tells me the maximum amount of X I can buy. And similarly, B over PY is the maximum amount of Ys I can buy if I don't buy any X. Okay, so there's my budget. And the slope of the budget line and the slope of the budget line equals negative PX over PY. And this is what's known as the marginal rate of transformation. It's the market's ability to transform X for Y. Okay. And if we've maximized utility, we're at U0 and we buy X0 and Y0. And you should know this from your basic microclass. Okay, so Utility is maximized at point A. Now I'm going to let the price of X fall. And what happens next is that our consumer then will change their bundle to achieve a higher level of utility. And we'll call that point C. So the price of X falls and we buy more X, X1. And we buy, in this case, a little less Y, Y1. Okay. Now, having the price of X fall meant that I was able to increase my utility, right? And you should be familiar with that. So I am better off when the price of X goes down. So I am, if that's the case, I am willing to pay to lower the price of X. So if I go to the original budget line, and then I shift the original budget line back, or the new budget line back around the original indifference curve, right? And I get, I'll call point D. And this, I shifted back, means that I'm at the original indifference curve, but at a new price ratio. The budget line is now flatter, but my utility is exactly the same. So what happens by lowering the price of X and then taking away income until you're back to the original indifference curve, I've effectively moved the consumer from point A to point D. So they've substituted Y for X, but kept utility constant, okay? And the amount that I shifted the budget constraint back measures the maximum I'd be willing to pay to get a lower price. So, oops. U1 minus U0 is going to be approximately equal to consumer surplus. It's the extra utility I get when the price of X goes down. Now, I've corrected for the extra utility by taking away budget to get you back so you're indifferent between the higher price and the lower price. So that I have A to D is equal to the pure substitution effect. And D to C is the pure income effect. And what it tells me is that there are two reasons people buy more good X. One, the relative price has changed and X is a bargain relative to Y. Second, a fall in the price of a good is like an increase in your real income. So my income is constant, but the prices are lower. I can now buy more and make myself better off. Okay. So what this tells me is that I can measure the willingness to pay in the budget constraint picture. Okay. So formally, if I want to maximize u of x and y, subject to b equals pxx plus pyy, then I find the partial derivatives, du dx, which is by definition the marginal utility of x, du dy, the marginal utility of y. And I take the ratio mux over muy, and that's the marginal rate of substitution, my willingness to trade y's for x's. And at the tangency point, MRS equals the price ratio. Okay. Now, what I can do is I can look at a couple of utility functions. So if I have the following, u equals x squared, y squared, then du dx is equal to 2x y squared, du dy is 2x squared y. Okay. Now, if I divide the first one by the second one, then I get the 2's cancel, the y and the y squared cancel, the x and the x squared cancel, and I'm left with y over x as the marginal rate of substitution. If the utility function is equal to simply x times y, then du dx, the derivative of the utility function with respect to x, is simply y, and du dy is simply x. And if I divide the first by the second, I get y over x equals the MRS. Now notice that the MRS for both utility functions is identical. So that means these two utility functions have the same preferences. So given a budget constraint, both utility functions, both people, if they're two different utility functions, would pick the exact same bundle because they have the same marginal rate of substitution. Okay. So consider the following example then. U is equal to x times y. And so we want to max U by the Lagrange method. So I set up my Lagrange utility function x times y plus lambda times b minus pxx minus pyy, because b minus pxx minus pyy is equal to 0. So this is simply equal to the utility function plus lambda times 0, which is the math trick that makes the Lagrange work. So when you add 0 to something, it remains the same. So the Lagrange method takes advantage of that relationship to create a trick for solving these kinds of problems. what we do is we take the derivative with respect to x, and derivative of x times y is y, minus, and it appears inside the budget constraint, minus lambda px equals 0. We take the derivative with respect to y, and we get x minus lambda py equals 0. And we take the derivative with respect to the Lagrange multiplier, and that just gives us back the constraint. Okay, now these are called the first order conditions of the utility max problem. If I take the first two equations, I can write them as y equals lambda px and x equals lambda py. If I divide the first equation by the second, the lambdas cancel, and I'm left with y over x equals px over py, or y equals px over py times x. So that I can substitute back into the budget constraint to get a final solution. So now I have b minus pxx minus py times y. But I know that y is equal to px over py times x from the MRS relationship. So now I simplify, and the py's cancel, and I'm left with b minus pxx minus pxx equals 0. 2pxx equals the budget. X star equals b over 2px. And that's the utility max value of x. This number I can stick back in and write y equals px over py times x. X is equal to b over 2px. And the px's cancel. And I'm left with y equals b over 2py. Okay. So this represents utility max bundle for both good x and good y. Okay. So x star equal to b over 2px and y star equal to b over 2py are known as the Marshallian demand functions, or what you call the ordinary demand. Okay. So these represent the two demand curves for x and y. And if you look at the formulas, budget's in the numerator. So as budget gets bigger, x and y get bigger. So they're both normal goods. And when the price of x goes up, quantity of x goes down, price of y goes up, quantity of y goes down, which is the behavior of a demand function. Okay. Now, if we substitute X star and Y star into the utility function, we know that U is equal to X times Y. So then we get equal to B over 2px times B over 2py. And that whole thing is going to be B squared all over 4px py. And I'm going to call that V. And this is referred to as the indirect utility function. And what it tells me is for a given set of budget and prices, what my utility number will be. So my utility directly depends on goods X and Y. So I gain utility directly from X and Y. But in order to buy X, I need a budget and a price. And to buy Y, I need a budget and a price. So indirectly, my utility depends on my budget and the prices I face, even though my utility directly depends on the commodities. Now, the next step we're going to isolate B. So we know that the indirect utility V equals B squared over 4px py. Or B squared equals 4px py V. And finally, B star equals the square root of 4px py V. This function is known as the expenditure function. Okay, and the expenditure function answers a very different question. So the utility function tells me the maximum utility I would get given the budget and prices I face. The expenditure function tells us the minimum budget needed to achieve a specific utility. Okay, so the expenditure function will tell me the budget I need to achieve a specific utility number. Okay, so let's work through this with an example. Okay, so let's consider, so the utility function gives me my indirect utility function, gives me my expenditure function, which I'm going to need for later. So let's consider the following situation. So we have a two good world, X and Y. And Y is known as the composite commodity. Or sometimes we referred to as all other goods. So I can buy X or I can buy other goods. If I buy other goods, then I'm buying Y. Okay, so initially, the market for X is closed. So I am consuming at point B. So I'm going to buy only Y or point B. Okay, so at point B, I have a specific level of utility. I'm going to call U0. Okay. Then I'm going to open the market for X. So the market for X opens at a price PX. So we come along and we say, now we're going to open the market for X at a specific price. And the consumer will then see that by having the market for X open, they can move to a higher level of utility. So they move to point A and they buy X0, Y0. Okay. So if I cannot access the market for X, I can only buy other goods. I'm at point B and my utility is U0. But if the market for X is open at a price of PX, I will trade down my budget line from point B to point A. So starting at point B, I will trade down the budget line till I get to point A and achieve the maximum utility capable. Okay. So I am willing to pay to open the market. And how much am I willing to pay? Well, let's consider that initially the price of X, the market for X opens, and I go to point A. And my utility jumps from U0 to U1. So if I was to pay money to get the market for X open, it would shift my budget line down as I paid to get the market open. The most I'm willing to pay is where I'm indifferent between the market being open and closed. And I'm having trouble here with the locking device. Come on, there we go. Okay, so if I give up budget, right? Hang on 1 second. I would move, we'll call that point Z, and I would move to X1. And I paid, this is the fee to open the market from B to point C. So I'm willing to pay from B to C out of my budget to have the market for X open. Now notice that I get the exact same utility. Point B and point Z give me the same utility, but at point B, I don't get any good X, and at point Z, I get X1. Okay. So this B to C, the willingness to pay for the market to be open, is referred to as my CV, compensating variation. So it is my willingness to pay for an economic change. I want to pay B to C, and I'll be indifferent between a market for X that's open and a market for X that's closed. Okay. So if I'm at B, the market for X is closed. The economic change is the opening of the market. So if the economic change occurs, I go to point A. My utility goes from U0 to U1, and I'm on a higher budget line. Well, now let's go back to point B and say, I cannot open the market for X, but I want you to be as well off as if we open the market for X. So I cannot open the market. But I want you as well off as if market opened. Okay. So if the market for X opens, you get a utility of U1. Now, how do I get U1 without opening the market for X? Well, I increase the amount of Y's while keeping X at 0. We'll call that point E. And if I give you B to E of other goods, then you're as well off at E as you are at A. So you're indifferent. And that's what's known as the equivalent variation. And if you look at the graph, and you can see that for this particular example, my compensating variation, which is my willingness to pay for the economic benefit, is C to B. So I'm willing to pay C to B to have the market open. Now, if I cannot have the market open, but you give me B to E in extra budget, I'm indifferent. So to me, getting a budget of B to E is equivalent to being able to buy good X at point A. And you can see in my graph that equivalent variation in this case is bigger than the compensating variation, even though both are meant to measure the same thing, which is the increase in utility from having a market opened. Okay. So now, let's consider a case where transit. Okay. So the government offers, so the bus fare is equal to, say, $4 a ride. Okay. So the price of X is 4. And at this budget, I can buy good Ys or B over 4 of X's. Okay. Based on the price of bus rides, I decide on which bus ride gives, how many bus rides maximize my utility. And I go to U0. Okay. Actually, I'm going to redraw that. It's not going to quite work for me. So the budget line comes down. Okay. And I get U0. And I'm at point A. Now, the government comes along and says, I'm going to offer you free bus rides. You can buy a bus pass. So you can buy a bus pass for F. And ride for free. Okay. So a bus pass, you take the budget away, you get paid, you have your budget minus your pass. That's how much money you have left. But once you have paid for the bus pass, then the budget line becomes completely horizontal. Oops. Sorry about that. And there we go. Okay. So if I buy the bus pass, then I can get to a higher level of utility at point B. Actually, I use B up for budget, so I'll use point D. Okay. Now, am I better off with the bus pass? Yes. What's the most I'm willing to pay in order to get the bus pass? Well, that would be given by a budget line that puts me back on the original indifference curve, but at the new price ratio. So the new price is 0. So I move to Z. So B minus F star is the most I would pay to get on the bus. So if I had to choose between $2 a ride or $4 a ride or a bus pass at F star, then I'm indifferent, right? Now, someone asked me, why is the budget line horizontal? Because once you pay for a bus pass, every time you get on the bus, it's free. So you do not have to give up any additional good Ys when you ride the bus, okay? Now, if you buy the bus pass and never get on the bus, then you are at this point, or this point, depending on which bus pass you buy. And you can have that much Y. And if you want to have X's are bus rides, you can just jump on the bus ride with your pass and you don't have to give up any more Ys. So the price of a bus, so the single ride fare is PX. The bus pass is known as a two-part tariff. So the net price is equal to your budget divided by the number of rides plus the price per ride you pay. But in this case, you pay 0 for each additional ride. You pay for the bus pass and, oh, sorry, the bus pass is not B, but F. So you pay F per bus ride and then it's 0. So for example, right, if the fee is $100 and you ride the bike 200 times in a month, then you pay 50 cents a ride. If the bus fare is $100 and you ride the bus twice, then you paid $50 a bus ride. If you pay $100 for your bus pass and then you ride the bus 1,000 times a month, then the price you pay per ride is 10 cents, okay? So hopefully that explains how the bus pass system works. Okay. So there's an example of a good where the price is 0. The budget line is horizontal. Okay. Now, let's work through a more complex numerical example. Okay. So we said from before, okay, U equaled XY, and the budget was PXX plus PYY. And when we max U, we got that X star was equal to B over 2px. Y star is equal to b over 2py. The indirect utility was given by b squared over 4px py. And the expenditure function b star was given by the square root of 4px py v. Okay. Now, we're going to use all of this information to calculate find the CV EV for a price fall. Okay, so we're going to let initially B equal 24, price of X is equal to 2, and the price of Y is equal to 1. Well, X star will be equal to B over 2px. B over 4 is 6. Y star is B over 2py, 12. And my utility number is 6 times 12 is 72. Okay. Now, I'm going to have the price of X fall. So B is still 24. Price of X is now 1, and the price of Y is now equal to 1. X star is 12. Y star is 12. And my utility is 144. Okay. So let's look at this graphically. There we go. Okay, so we start off looking at our X and our Y. And our initial budget line look like this. And 24 divided by 1 is 24. 24 divided by 2 is 12. And I'm at point A. And my initial X is 6, and my initial Y is 12. And my indifference curve is tangent at 72. So I'm indifferent, so I'm now maximizing my utility. Okay. Then the price of X falls from $2 to $1. Okay. Okay. So the budget line rotates out as the price of X falls. If I spend all my money on X, I can now buy 24 instead of 12. Now, as it turns out that X and Y are independent, so the price of Y never fell. Just the price of X. So my quantity of X goes from 6 to 12. Quantity of Y remains at 12. And my utility goes up to 24 or to 144. Okay, so I want to find CV and EV. And CV will be the old utility, new price of X. And EV is new level of utility, but at the old price of X. So we take the original budget line or the new budget line. So the price of X has fallen, but I am going to move you back to the original indifference curve so that you get the same utility as you got before the price fell. Okay. And let me just get this thing in place here. And come on. Okay. So no, this thing keeps jumping on me. Okay. I'm going to have to do it the old way. And I'll just shift it out this way. And I move to G. Now, I gave up this much income. That's my CV. So in order for me to get to point G, I had to take away income. So what is the budget I need to be at point G? So then I use my expenditure function. Okay. And it'll give me the budget needed for the new budget line. So I'm going to use U equal to 72, PX equal to 1. So that's a new price in the old utility. So we know that B star is equal to the square root of 4 times the price of X, 1, price of Y, 1, and utility, 72. Okay, which means it's equal to 2 times the square root of 72. And that number is approximately 16.97. So the budget I need to be on the new lower line is B0 equals 16.97. So my CV will be 24 minus 16.97. So that is going to be, 1 second. $7.03. So that's my CV. The willingness to pay. I'm willing to pay $7.03 to get the lower price of X. So that guy is 7.03. Okay. So now I know what the compensating variation is. Now, if I want to find the equivalent variation, the equivalent variation is going to be the old price, new utility. So for EV, use a utility equal to 144 and a price of X equal to 2. So I need to find a budget line that has the price of X equal to 2, which is the slope of the steeper budget line. But so I'll go to point H. So EV is to increase your budget so that you're on the new indifference curve. So I'm on the new indifference curve, but at the higher old price of X. And that gives me point H. So how much budget do I need to get to point H? So I know that the budget B star is 2 times the square root of PX, PY, and U. So now I just need to substitute in, and I put in 2 times the square root of 2 times 1 times 144, right? So that's going to give me a new number, which will be 33.94. That's how much budget I need to get to the higher indifference curve, but when the price of X is $2 instead of $1. So this difference in here, this is my EV. And the line, the budget line here, is a budget equal to 33.94. And in order for me to get there, I needed to get my EV, which is going to be 33.94. That's the new budget minus the original budget of 24 equals 9.94 extra dollars. And that would move me from point A to point H. So For doing compensated variation, you take the original indifference curve, but the new price line. That is what you need. Old utility, new price for CV. For EV, we take the new indifference curve, but at the older, higher price ratio. And that gives me the equivalent variation. So how much am I willing to pay to get the price of X lowered? I'm willing to pay $7.03 to get the price of X lowered. However, if I can't get the price of X lowered, and you gave me instead $9.94, I would be as happy as if the price of X had fallen. Okay. So now, last thing, okay, is I am going to put two graphs, one under the other, to put this story finally together. So I have good X and good Y. And in the top picture, I'm going to have my high price of X to start off with. Come on. So here is my original budget line, and I go to a point like A. Then my budget is reduced. So the budget line rotates out. And I move to a point like C. Okay. Then I take away budget to get you back to the original indifference curve. Hang on one second. Yep, there we go. And with the original indifference curve, I would move to point G. So my original indifference curve started at point A and then moved down to G. So that's U0. Then, if you hadn't taken away any income from me, I would have moved up to point C. And that would be U1. Okay. If I bring my original X down to X0, then X0 is point A, and that is the price of X 0. So that's a point on the demand curve. Then the price of X falls, and I go to X1. And since the price is lower, I'm at PX1. I am at point C. So points A and C represent 2 points on the ordinary Marshallian demand curve. So we call that the Marshallian demand. Okay. Now, if the price of X fell, then the area P0, AC, P1 so that area PX0, A, C, PX1 is consumer surplus. Okay, so the change in consumer surplus is the blue area under the ordinary Marshallian demand curve. Now, if we go to point G, then I'm consuming X2. X2 is at the same price as C. So there is G, same price, but a different quantity. And if I go from point A down to point G, I get DC, and DC equals the compensated or Hicksian demand. Okay, so Alfred Marshall was the economist often attributed for developing the supply and demand curve story. Sir John Hicks was an economist who looked at the issue of income and substitution effects and compensated versus uncompensated demands. So now, when the price of X falls, I move from point A down to point G. I am buying more X, but my utility is staying exactly the same as it is at point A. So point A to point G is same utility, different set of prices. So the yellow area, so the area PX0, A, G, PX1 equals CV. So consumer surplus is slightly bigger than CV. If, on the other hand, I was to look at EV, which is the higher budget line, steeper budget line on the original indifference curve, or on the new indifference curve, which is up here, right? And at this point, I'll call that H. H gives me X3. And I bring X3 down. And put it in the graph. It's the same price as A, but further over. And if I connect those 2 points, and this is H, then I have another compensated demand curve at the higher price. And if I take the area under this new higher demand, I have equivalent variation. So this is what's referred to as a normal good. So CV is less than consumer surplus, but it's less than EV for normal goods. And those are goods you buy more of when your income goes up, not the price. When your income goes up, you buy more. That's a normal good. If your income goes up and you buy less, it's an inferior good. So for inferior goods, CV is greater than consumer surplus, which is greater than EV. So the reverse is true. Okay, so CV and EV are two welfare measures. In fact, consumer surplus, CV, and EV are all measures of welfare. Okay, so we will use CV, EV, and consumer surplus to evaluate environmental goods. Okay, so I am going to stop it here. Okay.